Hi, everyone. I'm Dan Spielman, and today it is my privilege to introduce Nicholas Christakis. We are co-directors of the Institute for Network Science, so probably everyone here knows Nicholas, or at least has followed him as a voice of wisdom on the COVID era, both how to deal with it and what we should expect. Apparently, that's not what he's going to tell us about today, unless I'm missing it. But before we get going, I want to mention one interesting fact about Nicholas. So if you look around Yale, look at the directory of professors. You see there are many people with titles like professor of some department or named professor of some department. But Nicholas is the Sterling Professor of Social and Natural Sciences. And I have no idea how he managed to get a title so cool. I'm hoping that it has something to do with a network intervention that we'll now learn about.
Later, I'll tell you the story privately later. Anyway, thank you, Dan, for that introduction. It's been a wonderful joy for the last 10 years to have this duty with Dan and to get to know him and to learn from him and to go with him with some of my crazy thoughts about all kinds of topics. And I think this is cross-listed, these remarks are cross-listed with the new fantastic Institute for Data Science, for the Foundations of Data Science, which is a really exciting development at Yale that I'm really happy to see. So I'm going to talk today in an overview way about a sweep of topics and research that has been done in my lab over the last 15 years, and hope to frame for you what I would consider to be a deeper understanding of the structure and function of human social networks. Because humans are embedded in these networks, and they obey very particular mathematical, biological, psychological, and sociological rules and principles. And taking those rules and principles into account gives us new opportunities to gain insights into our behaviors, and also insights into how to change our behaviors. We can use an understanding of social network structure and function to intervene in the world to make it better, to improve our health, our wealth, our security, and our everyday life. And in the broadest sense, taking our embeddedness in networks seriously shifts our gaze away from the targets of the intervention to everyone around the target. It's like an exercise in the study of externalities within economics. How can we understand the response to treatment, not just among the treated, but among the untreated? And that's actually kind of a radical shift in broad branches of medicine, public health, and actually even in the social sciences. So let me see if I can, we've had some problems here. Aha. So I'm interested in real social networks, the kind that human beings have been making and embedding themselves in for tens of thousands of years, and not just the recent online variety. And real social networks look like this. Every dot's a person, every line between them is a relationship of some kind, who's friend or neighbor or coworker or whatever. And these things, to my eye, when I first started mapping networks like 20 years ago, I was immediately struck by how beautiful they were, because they are beautiful, and they're intricate, and they are elaborate, and they are complex, and in fact they are so ubiquitous in the world that one has to wonder, what purpose do they serve? I mean, why are we embedded in networks? How do they form? How do they work? And how do they affect us? And I've spent 20 years studying how and why human beings form social networks and how they affect our lives, our health, our desires, our feelings, our thoughts, and our actions. So part of this work has involved exploring the biological predicates and consequences of social networks and the evolutionary basis for social network structure and function. And probably everyone in this audience knows, but just to fix ideas for some of the other things I'll be saying later in the talk, there are a number of ways that you can characterize the structural position of individuals within a network. If this is a group of 105, this is a real group of 105 people and they're real friendships. And you can see that different people occupy structurally different positions within the network. And you can characterize this in a number of ways. Three of the simplest are shown here. So for example, node B has a degree of 4, has 4 connections, and D has 6 connections. This is just the degree of a node, or the number of connections it has. And that's pretty straightforward, and people might know that about themselves. You have 10 friends. You know you have 6 friends. I have no friends. People know this about themselves. They know their degree. But we can also look at nodes C and D. C and D both have 6 connections, and this might be the limit of their understanding of where they are in a social network. But we, with a bird's eye view, can see that C and D are very different. And I can cultivate this intuition in you by asking you, who would you rather be if a deadly germ was spreading through the network? It's obvious it's better to be D. D is on the edge of the periphery of the network, is less likely to get whatever's spreading or to get it early in the course of the epidemic. And this is known as the centrality of a node and can be quantified mathematically in a variety of ways. The way that I like that is most intuitive to me is between the centrality, but there's eigenvector centrality. There are lots of ways of doing it. And finally, if you look at nodes A and B both have 4 connections, but the difference between the two is that A's friends are friends with each other, whereas B's friends are not friends with each other. And this is known as the transitivity of a node. And in one of our first studies of the biology of this phenomenon, this was published now 13 years ago, we did what's known as a twin study where we compared the networks of same-sex dizygotic twins to monozygotic twins. And we found that 46% of the variance in the number of connections that a node had could be explained by the person's genes. Now, that's not very surprising. That just says some people are born shy and some people are born gregarious. People vary in their taste for friendship. But we also found that 47% of the variance in people's transitivity could be explained by their genes. And this is a very bizarre result, one of the most bizarre to come out of my lab in the last 20 years, because what I just told you is that if Tom, Dick, and Harry are in a room, whether Dick is friends with Harry depends on Tom's genes. Whether you two are friends with each other depends on her genes. And we think this arises from a variation that people have in their tendency to introduce their friends to each other, which natural selection probably shaped, and I discuss in a book of mine called Blueprint. Finally, even 29% of the variation in your centrality can be explained by your genes. And here we think this arises because of variation in whether people like to befriend popular or unpopular people. And you can imagine good reasons to do both, to befriend popular people or unpopular ones. So where you are, so the fundamental reality of our desire for connection and our susceptibility to influence, it turns out, has always been with us. And where you are in the vast fabric of humanity depends in part on your genes. And our lab has been amassing evidence that it is indeed not a coincidence that we form networks with particular properties. And we have shown that there's an evolutionary significance to and heritability of social network structure and function, and that phenomena like peer influence and even homophily have very ancient and fundamental significance. And across evolutionary time, it must have been the case that the benefits of a connected life outweigh the costs, and that natural selection shaped the structure of our networks, just like it has shaped the structure and function of our bodies. Now, if social network structure has genetic antecedents and evolutionary significance, it begs the question of how ancient this structure is and whether we could document such structural features in human populations living in non-modernized settings. So what we wanted to know is, look, if we could go back 10,000 years and study the humans that lived then before modern technology, if in fact there's something intrinsic in the mathematical structure of graphs that we humans inescapably make, those humans should have networks similar to ours. Of course, we couldn't do that. So instead, we hit upon the idea with a former postdoc of mine, Corinne Apicella, this paper was published 10 years ago now, to map the social networks of the Hadza hunter-gatherers. There are only about 1,000 of the Hadza left. They live like we did during the Pleistocene. They have no material possessions to speak of. They sleep out under the stars. And what we did is we made a photographic census of all living adult Hadza, the kind of Hadza Facebook. We printed their photographs working with ethnographers of the Hadza. And Corinne, where is she? Here's Corinne, took these into the field and just would sit near Lake Ayasi and wait for a Hadza person to walk by, because you can't make an appointment with a Hadza person. You just have to wait till you see one. And then she would say, excuse me, who are your friends? Then they would identify their friends, thank you, they'd move on, and then she'd wait for another person and on until we were able to amass data to map the social networks of the Hadza. And these networks that the Hadza make look just like ours. Visually and mathematically, any kind of analytic tools you might want to throw at these networks, look at degree distribution, transitivity, degree assortativity, decay with geographic distance. You go on and study the Hadza networks. They're just like ours. So despite the fact that in the intervening 10,000 years, we've invented agriculture, we've invented cities, we've invented telecommunications, the structure of the networks that the Hadza make are like ours. And incidentally, while we were there, we had the Hadza play. This paper was published 10 years ago now. we had the Hadza play a public goods game. That's a kind of paradigm drawn from behavioral psychology, behavior and economics, where people are invited to share resources with those around them, and we can then quantify how cooperative those individuals are, and we quantify their cooperativity, and the color and size of the nodes indicate that, and you can see that there are clusters of cooperative and non-cooperative individuals within the network. And this actually relates to the structure of human social networks, and I'll come back to this idea in a moment. This phenotypic clustering, particularly of pro-social goods, like cooperation. The fact that cooperative people tend to be near each other in the graph is not a coincidence, and is fundamentally related to network structure and function. Anyway, in a parallel and early stream of work that started in 2001, using, actually in 1998 it started, using both observational and experimental methods, we and others have provided evidence that a variety of behaviors and phenomena beyond germs, which we've all been obsessed with lately, spread within networks, and they do so beyond just dyadic ties via social contagion. So it's not just that I affect you. We can document that when I affect you, you in similar ways affect him, and then he affects her, and so on. We call this the 3 degree of influence. It's a sort of a stylized fact, observation about social phenomena. And we found evidence that it pertains to obesity, smoking, drinking, and drug use behavior, emotional states like happiness, loneliness, depression, and altruism. This is one of our first experiments. I'll show you that in a moment. Also criminal behavior. There was a wonderful social scientist here, Andrew Papachristos, who did a ton of work in this area. He's now gone to Northwestern. Voting, a massive experiment of 62 million people, also published in Nature, showing that voting cascades can be documented, actually induce purchasing behavior and ideas. People's attitudes, decisions, and behaviors depend in quantifiable ways on the attitudes, decisions, and behaviors of others to whom they are directly or indirectly connected. And a key idea about networks is that they magnify whatever they are seeded with. Social networks magnify whatever they are seeded with. They function like a social magnifying glass. If you put something in a network, it'll make more of it. But the network is agnostic. It'll magnify fascism and Ebola and sadness and corruption. But equally, it will magnify kindness and love and happiness and ideas. But it must be seeded. Some exogenous force must like start the cascade going, like a rock dropped on a surface of water. Once you drop the rock, then you get the waves that propagate. But there has to be a hand dropping rocks before the network will kick in and give you more of whatever it is that you've put in it. Now, there's of course a lot more going on than just social contagion or induction in networks. So if you find that there's clustering or similarity, if nearby nodes in a graph have similar traits of some kind, one possibility is a kind of induction or social contagion, a kind of spreading process in the graph. I'm happy and it makes you happy, and then you become happy. Another totally different possibility is homophily, or love of like, or birds of a feather flock together. Here the idea is that it's not that my weight gain causes your weight gain. Here the idea is that we both form a friendship because we have a similar body size or interest in running to begin with. And because of that shared interest, we form a tie because of the trait. We don't develop the trait because of the tie. And a third possibility is context. Here the idea is that it's not that my weight gain causes your weight gain, not that you and I form a connection because we have a similar body size, but we share an exposure, a joint exposure to something like a gym or a fast food joint that makes us lose weight or gain weight at the same time. All three of these are typically present in any social phenomenon. Why are your children studious? Is it because their friends are studious? Do the brainy kids like us hang out together? Or do they have a charismatic teacher like Dan Spielman that inspires them? And so they all get smart at the same time. So really to sort this out and see, is it Dan that's doing it? Or did you guys do it? Or did it spread? We need experiments to do experiments. And so beginning in 2008 to 2009, approximately, my lab switched to doing almost exclusively experiments for the last 13 years. This was the first experiment we published 12 years ago now. In this experiment, we brought college students together, and they were strangers to each other, and they were randomly assigned to groups of 4 people, and they were given a little bit of money, and they were invited to play a public goods game, where if they contributed some of their own personal resources to the group, it was doubled and then divided amongst everyone. So you give up $1, it becomes 2. Each of your friends gets 50 cents. You get only 50 cents back, so you sacrifice 50 cents, a cost to you, but the group has gained wealth as a result. Obviously, the most rational thing to do is for everyone to give maximally. If that happens, everyone is doubling their money every round. But of course, from an individual point of view, what you really want to do is give nothing and hope that everyone else gives money. What we did in this experiment is we put them into these groups, and then a bell would ring and they'd be randomly assigned to new groups, and a bell would ring and they'd be randomly assigned to new groups. And so we created artificial linear networks such that we could create a cascade of people, such that A had previously interacted with E, I, and M, and E had previously interacted with F, G, and H, and so on. And as a result of that, we were able to document the following thing. We were able to show experimentally that if Eleni is kind to Lucas in period 1, Lucas is kind to Erica in period 2, Erica is kind to Jay in period 3, and Jay is kind to Brecken in period 4, that the behavior spreads to 3 degrees of separation here in this experiment. This could not be due to context or to a homophily. It had to be due to induction or social contagion because it was done experimentally. And in fact, this is another one of the most bizarre results to come out of my lab in the last few years, because what I just told you is that how Jay treats Brecken depends on how Eleni treated Lucas, even though neither Jay nor Brecken ever saw Eleni or Lucas. How you two treat each other depends on how you two treat each other, even though neither of you know either of them, right? A cascading process through the graph, action at a distance, right? Happening in the geodesic space. And this geodesic spread of influence is distinct from the temporal persistence. So that if Eleni is kind to Lucas, Lucas learns to be kind. And he's kind to Erica in period 2, and Lysander in period 3, and Benny in period 4, and so on. And in fact, if you fold back all the downstream kindness, for every extra dollar that Eleni gives Lucas, you get 2 more dollars that appear within the graph. Networks magnify whatever they are seeded with. So when Eleni is nice, it creates positive ripples through the graph that can be induced and observed here experimentally. Now, to be clear, we're affected in another way by social networks. And this is a metaphor that I started using 20 years ago now. And I was so surprised to discover that it didn't seem to be widely used before, but it's just such an obvious metaphor for me, which is that it's not just what's happening around us that matters, it's the actual structure of the network that also matters. And if you think about these two objects, as they're both made of carbon, as you all learned in high school chemistry, and the difference is in how the carbon atoms are connected to each other. You take the carbon atoms and connect them one way, you get graphite, which is soft and dark. Or you take the same carbon atoms and connect them another way, you get diamond, which is hard and clear. And there are 2 key intellectual ideas here. First, these properties of softness and darkness and hardness and clearness are not properties of the carbon atoms, they're properties of the collection of carbon atoms. And second, which properties you get depends on how you connect the carbon atoms to each other. Connect them one way, you get one set of properties. Take the same carbon atoms and connect them another way, you get a different set of properties. And it's the same with human groups. You can take a group of people and connect them one way, and they are nice to each other and innovative and communicate effectively and coordinate and cooperate. Or you take the same people and healthy, or you take the same people and connect them a different way, and they have none of those desirable properties. So it's not just spreading processes on graphs that matter. The actual topology of the graph is also highly relevant to human experience. So here's one of my favorite examples. This is Brian Utzi's work. Brian, about 20 years ago now, became unaccountably obsessed with the success or failure of Broadway musicals. He actually grew up in the Garment District. His parents were poor immigrants from Eastern Europe, I think. He was near the Broadway musicals, and he became obsessed with this. And he put together a data set of 326 Broadway musical production companies, the actor, the director, the musicians, the producers, and so on. And he mapped the connections in those companies, and he computed the density of the connections, something similar to transitivity that I introduced earlier. If you take this person and they have 5 connections, none of those other connections exist. You've got 0 out of 10. And there are 10 possible connections, 5 times 4 divided by 2. None of them exist here. 4 of them exist here, and all 10 of them exist here. And for each Broadway musical production company, he computed the density from 0 to 100%. And then he quantified the success of the show, either by the fraction of positive reviews or by the amount of money that the show made. And he found that if nobody knew each other from before, the show was a flop. And if everybody knew each other from before, the show was a flop. And optimal productivity was achieved when you had middling level of density. The ability of this group to be creative, to manifest this emergent property. I mean, this notion of emergence is one of the deepest in science, in my view, and arises in biology and chemistry and physics, in social science. So this creativity you see is an emergent property of the structure of the graph, in a sense. So the structure of the network also matters. And I have to show this because this is one of the joys of coming to Yale for me, was that I was put here near all these other people like Dan and Amin and Drago and Leandros and all these electrical engineers that I started talking to, which hadn't been a part of my prior experience. And so we started publishing other papers, took me in new directions I didn't expect. This is a paper we did with George Christakis, who's not here anymore. And what we did is we had data on a new monetary instrument called Sardex, which was a mutual credit system, a kind of community, like an abstract community currency that was invented and deployed in Sardinia during the financial crisis in 2010. And we were able to get from the people that were running Sardex detailed information regarding many millions of euros of transactions in 2013 and 2014 among over 2,000 firms that were trading in this currency. And this image just shows a super network of nodes where every node is a city in Sardinia, and the lines represent money flows between those nodes at the city, at the metropolitan scale. But we can actually map the network at the firm level. And so every dot here is a firm, and we have directed graphs of money going. So you give me goods, I give you money. And then you take the money and buy goods from her, and so the money goes to her. So you can track the flow of money and goods in this system. And we resurrected and expanded some old ideas from networks about something called cycles or K-cycles within graphs. So for example, this is a linear path through the network, 1, 2, 3, 4, degree 4. And this is a cycle through the network of 1, 2, actually, let me find a shorter one. Is there a 4 cycle? No, they're all bigger cycles. Anyway, is there one?
On the far left here,
on the
3 cycle.
There's a 3 cycle here, and then here's a 1, 2, 3, 4, 5, a 6 cycle, and so on. And so we were able to quantify what your K cycle centrality was. How many cycles of degree 3 or path 3 were you on? How many cycles of path 4 were you on? How many cycles of path 5 were you on? Certainly for those that are bigger and bigger, you should be unaware. Like this guy here doesn't know that these two people far away from him are connected. And yet the fact that he's on this cycle is highly relevant to his economic productivity. In other words, the success or failure of this firm depends on whether nodes far from him have united to create a cycle. Because in this type of a system, sinks of debt or credit are a killer to liquidity, right? Like if you accumulate a lot of cash or you accumulate a lot of products, you're not lubricating the economic system. And we were able to show that for individual firms, the success or failure of those firms depended on the structure of the network, here quantified as their K-cycle centrality. Okay, that's like a whirlwind. And how long did that take me? Almost 24 minutes, far too much. Of like 20 years worth of work that brings us to this stage, which is that this set of projects suggested to us that there might be 3 ways of intervening in social networks. We could manipulate connection and change the structure of the graph. We could manipulate contagion. It's okay, there's the structure of the graph. How can we change the flows within the graph? Or we could manipulate position, which is changing the location of individuals within the graph. Same structure, same individuals. Where do you put the people in the graph? And how does that affect the emergent properties of the graph? And there's expanding science in all 3 areas using both online and offline settings. And I want to give you a feel for some of our results. All of these are experiments, which I'm going to show you. To do this work, we were very fortunate to have some software developed in my lab by Mark McKnight and Wyatt Israel, which we call Breadboard. We've made this publicly available. this software allows you to create, it's integrated with Amazon Mechanical Turk. And so you can create temporary artificial societies of real people, recruit thousands of research subjects that you pay small amounts of money to, and then drop them into these little virtual environments that you create. And so you can, in a godlike way, do experimental science on human groups, large numbers of people in large numbers of groups. This is one of the first experiments that we did, published now 11 years ago. In this experiment, where we're manipulating connection, we drop people into a graph. This is about 20 people in an Urgis-Renyi random graph with 30% tie saturation. And we introduce them to their neighbors who are arbitrarily chosen. And they had to play a public goods game like the Hadza that I mentioned earlier. They had to give money to their neighbors and then everyone would benefit, but maybe the neighbors would defect. The kind cooperative people are in blue and the defectors are in red. The defectors didn't give any money, just hope that other people would give them money. In the branch of the experiment where we put hundreds of people into dozens of groups that was fixed. So we dropped these people into the group and they played multiple rounds of the experiment to 10 rounds. By the end of this experiment in the fixed graph, everyone had become a defector, except these few cooperators here who were sort of on the edge of the network, keeping civilization alive, kind of cooperating. And this is, again, like the high school science projects we were all in. I'm the teacher. I say, okay, you four are going to work together in a group. You're a very good student and you work hard, you're doing all the work. And they say, you know what? Let's let him do the project. We'll do nothing. And so you get really pissed, right? Because they're all defecting and you're doing the work and you have limited options. Either you do all the work and they also get credit, or you also get lazy and stop working. And that's what happens here. When people get exploited, eventually they all become defectors. In a different branch of the experiment, we manipulated the rules of engagement and we allowed people a modest level of rewiring. At every time step, in addition to choosing whether to cooperate or defect, they could also choose whether to remain connected or to disconnect from others. And in that branch of the experiment, everyone or most people stayed cooperative. The point is, I can take you people and I connect you one way and you're nice to each other. Or I take you same people and I connect you another way and you're mean sons of bitches to each other. So it's not the people that are so important. It's the connection between the people, the structure that can guide what happens in this type of a situation. In a subsequent experiment that Hiro Shirado spearheaded in my group 9 years ago now, we, based on some theoretical work that Feng Fu, who's an applied mathematician at Dartmouth, a former postdoc of mine, had done, Feng theorized that this should be parabolic, this relationship between the rewiring rate, the social fluidity, and the cooperativity on the y-axis. And what we found is that actually, if there was social rigidity, if everyone was stuck with everyone else, then cooperation was low or disappeared. But if it was maximally fluid, cooperation also disappeared, and that the optimal cooperativity was achieved in middling levels of social fluidity or social rewiring. And this result actually makes sense if you think about it, because you don't want too much social fluidity either, because then also people stop investing. Imagine you are in Russia and you are assigned to a house, or you're trapped in some kind of American high poverty neighborhood, and all of your neighbors are throwing their garbage and putting graffiti and neglecting to take care of the environment. Well, then you also become, you don't take care of the environment. Why should you clean the sidewalk in front of your house if all your neighbors are throwing garbage out? Conversely, if you have new neighbors every day, right? If every single day new neighbors are assigned, you also have no incentive to go and take care of the commons. So you want people to have some fluidity, but not too much. Many social institutions are like this. Think about a country in which no divorce is possible. If your spouse is abusive to you, you can keep being nice to your spouse forever and ever, or you also become abusive or neglect your spouse. Conversely, if divorce is too easy, and you can have a new spouse every day, you say, I divorce you and I'll marry her, I divorce her and I marry him. Every day you just marry someone else, you also don't make investments. So you want social institutions that move the fluidity of the ties to the middling part of the regime. By the way, we have similar things with housing policy in our country that incentivizes people to kind of stay in their neighborhoods, but doesn't lock them in, right? They can move if they want to. In still another experiment of ours, now I'm coming forward now in time, published in 2015, This work spearheaded by Akihiro Nishi of my lab, who's now at UCLA. What we did is we, again, used one of our canonical kind of breadboard games, a public goods experiment. People were dropped into graphs. And here, everyone had been talking about economic inequality and its impact on social order. And I, given my left-wing politics, I had just assumed inequality would be really bad for social outcomes, for welfare, for collective welfare. And I said, let's do some experiments. So we created artificial worlds with inequality, with real inequality. We gave people real money, but we varied it. Here, the size of the dot is the amount of money people have, and the letter indicates whether they were rich or poor at the beginning. So we created some worlds in which the Gini coefficient was 0.4, okay, which is actually United States or Moroccan levels of inequality. We also created other worlds in which we had like Scandinavian level of inequality, Gini of 0.2, for example. And they played their public goods game. And what we found was that in a situation in which they could not see each other's wealth, we could drive down the inequality by the end. So inequality went from 0.4 to 0.14, and most of the people are blue dots, they're cooperative, and all the dots are big. A lot of wealth is created, a lot of cooperation is created, a lot of inequality is lost in a situation in which people cannot see each other's wealth. But then we flipped a switch in a different branch of the experiment, and now people could see how much wealth their neighbors had. And in that situation, the society collapses. You have many more defectors, less wealth creation, and sustained inequality. So in this experiment, we manipulated both the initial levels of inequality, none, everyone had the same wealth, low, 0.2 Gini, high, 0.4, and whether wealth was visible or invisible. And then on the x-axis here is the rounds of the game, and on the y-axis is the average wealth that was produced by these societies. In these 6 groups, everyone starts at the same place, but then they have divergent fates. And what we found, which really depressed me, is that the amount of inequality wasn't the big deal with respect to wealth creation, but visibility was. So the solid lines, the wealth was visible, the dotted lines, the wealth was invisible, and the invisible worlds all outperformed the visible worlds in terms of wealth creation. And they also outperformed in terms of cooperation. It wasn't inequality that crushes cooperation, amazingly enough to me. It's visibility of inequality that crushes cooperation. So another structural feature of networks, whether you can observe traits of your neighbors, is relevant. One more result in connection, and then I'll move on to contagion and then position, and we'll, I think, given the speed with which I'm talking, end on schedule. So this is another experiment that was prompted by my hanging out with electrical engineers. And I don't know whether this is still popular, but about 5 or 10 years ago, everyone was really interested in the sharing economy and were there ways to optimize sharing. So we tried to invent a game, a scenario that we could use in the breadboard to do experiments with sharing. And we created what we call the Wi-Fi sharing game, where people were endowed with a resource that if they didn't use it, it was useless to them, but it could be valuable to someone else. So for example, when you guys aren't at home right now, you have broadband at home, maybe you should share it with your neighbors, right? Your neighbors could use that broadband. It doesn't cost you anything. They're using the broadband, but then when you go home tonight, maybe your neighbor's away and you could use their broadband and get more access to the internet or whatever. So it's a different kind of economic payoffs. In this situation, we drop people onto a 2x2 planar network. We vary the degree of the Wi-Fi router, the distance that the Wi-Fi router could be effective, which then creates different graphs, right? If you expand the distance of my Wi-Fi router, I get more connections and they get more connections. So we could create these networks. And then we did that and we published a paper about that, but then we used that platform to do another experiment, which revisited this issue of carbon that I mentioned earlier. And what we did is we, in this new experiment that was published now just 3 years ago, in this experiment, we dropped 15 people into 2 different, experimentally. Some were dropped into one network, some were dropped into another network. These 2 networks all had 15 people and all had 18 edges. Furthermore, they had the same exact degree distribution. In both networks, there was 1 node there were 6 nodes that had degree of 1, 3 nodes that had degree of 2, 3 nodes that had degree of 3, and 3 nodes that had degree of 5. Okay, so the number of ties, the number of nodes, and the degree distribution is the same in both networks. But we experimentally manipulated a different high order property of the network, which is whether the network was degree assortative or degree disassortative. In this network, popular nodes are connected to popular nodes and unpopular nodes to unpopular nodes. And in this network, popular nodes are connected to unpopular nodes and vice versa, okay? And then we had them play their sharing game, the same exact game that we did before. The people in this experiment can't tell the difference between what world they are in. And what we found was that the collective welfare was improved by arranging the networks to form ties between people with similar degree, even without increasing or redistributing resources. We could make people happier by turning up this property of human social organization, which is that popular people befriend popular people and unpopular people befriend unpopular people. This is a natural property of human social groups. And it turns out that this property has many benefits to us. One may be enhancing our satisfaction with social exchange. Another actually may be in tamping down on the spread of pathogens. So in other words, I can take you people, and you all have whatever immune systems you have, and I can have a budget of 50 ties, and I can arrange those ties in a way that makes epidemics very easy, or I can arrange those ties in a way that makes epidemics very difficult. In other words, I can endow you with a collective immune response, not just with an individual immune response, by manipulating the topology of the network. And it turns out that degree assortativity is very good for preventing epidemics from taking root in a human population, where degree disassortativity is bad. The point is, once again, that is the carbon example, that the structure of the network matters. Okay, in a different paradigm, we did some experiments manipulating contagion. Here the idea is, imagine you have a village or a school or a firm or a classroom, 100 people here, and then you have enough money to reach these 6 people shown in the yellow dots here to teach them like a public health intervention, like about latrines or vaccination or mask wearing or whatever you want to teach them. The ordinary perspective in public health is you teach those 6 people to wear masks, you come back a year later and you see what fraction of them are wearing masks, and you see that 3 of the 6 are wearing masks. The response to treatment among the treated. That's not what I'm interested in. I'm interested in the response to treatment among the untreated. I want to know, what does everyone else in this village do when you treat those 6 people and teach them to wear masks? Maybe if you pick 6 people at random, 3 of the 6 start wearing masks, they persuade 3 of their friends to wear masks, or they influence. A total of 6 people in this village are mask wearers a year later. And here in the untreated village, by secular change, maybe 2 people adopt. And the difference between 2 and 6 is the experimental treatment effect of teaching these 6 people whether to wear masks or not. But you should have the intuition that maybe it's good for me not to pick these 6 people. Maybe we should just pick these 6 central people. Maybe once again, you teach these 6 central people to wear a mask. 3 of the 6 adopt mask wearing, but maybe 30 of their friends adopt. Same village, same number of people targeted, same intervention, 10 times the effect because of how you pick these people in this situation. Now, you could also, and I'll just set the stage because we just published a paper about this, you could also imagine that there's ways to manipulate networks, not just to enhance the response to treatment among the untreated, but to enhance the response to treatment among the treated. So for example, let's say again, 6 people chosen at random, they're far apart from each other, 3 of the 6 adopt the practice, or you pick a cluster of 6 people and treat all 6 of them, maybe 5 of them would adopt. So you can enhance response to treatment among the treated, not just response to treatment among the untreated, by shrewd selection of the nodes. Now, mapping a social network is not always possible or feasible. And so if this was to work, and I first came, actually this was 10 years ago, I came in to talk to Dan. I said I had these crazy ideas about different sorts of network targeting. We'd actually already done one project before that. And one of the ideas I went to Dan with was about using k-corners. Like, could you use k-corners to pick a reduced set of nodes within the graph that you should target? The problem with it, and Dan and I had these conversations. I got very excited. I got persuaded it would be really effective. But of course, to do that, you have to be able to map the graph, which is expensive and time consuming, especially in developing world settings. So while that might work in online settings, in the world I was working in, it wasn't as good. So we needed something else. And one of our ideas was to take advantage of this thing called the friendship paradox. So raise your hands if you've ever heard of the friendship paradox. Friendship paradox is a really cool property of human social networks, or actually any networks with heterogeneous degree, which is that your friends have more friends than you do. Did you know this? Your sexual partners have more sexual partners than you do. And in what is the most depressing to me, your co-authors have more co-authors than you do. That's a knife in my heart. So anyway, so if you pick people at random and have them nominate one of their friends at random, you go from the 6 yellow dots to the 6 orange dots, the average degree and the centrality of the orange dots will be higher than the average degree or centrality of the randomly chosen dots. So the average node in a graph has mu, the average of the degree distribution friends, and the average friend of the average node has mu plus the variance in the degree distribution divided by mu possible friends. And I can cultivate this intuition in you initially, or there are a number of ways, but one way is just to invite you to consider the boundary condition, which is all the nodes on the periphery. They're on the periphery because they only have one friend. And their friend must necessarily have 2 friends, right? So for every dot on the edge, their friends have to have more friends than they do. And it turns out that's a property all the way through. This is also related to something known as the class size paradox, which I don't have time to go into, but it's kind of cool that they're related to each other. The class size paradox is that you guys all think that classes at Yale are huge, whereas the dean looks at the list of class sizes and says average class size is 20, and says class sizes are small at Yale. Well, the reason, of course, is that big classes have many people, so more people respond that they have big classes. So anyway, look it up if you're interested. There's a whole Wikipedia entry. I see some quirky looks. But the thing about the friendship paradox that's so cool is that you can find the orange dots without mapping the network. You just go into a village, ask people, pick people at random, ask them who their friends are, and treat their friends with a public health intervention. And so you don't have to map the network to make it work. We've been doing a number of projects on this for over 10 years now. We've done many large-scale field experiments in challenging settings. This is one place we work in Honduras. People here live on about $2 a day. This is mountainous country. Mark McKnight in my lab and Wyatt Israel and a bunch of undergrads over the years have also helped develop this other software, which we make publicly available, which allows you to map networks we call Trellis. It's battle-hardened tablet-based software you can take into the field, and you can photograph people and then use it to sociocentrically collect data. And in one of our first projects, which was published 7 years ago now, we mapped the social networks of 32 villages in the central highlands of Honduras. And then we picked nodes according to different targeting algorithms. So this illustrates one particular village. These are the, I don't know, 6 or 7 nodes that would be picked if you picked the nodes at random, compared to the 6 or 7 nodes that would be picked if you picked the nodes with the highest degree. And so now we could randomly assign villages. This third of you, these third of the villages, people, I forgot if it was 5, I think, yeah. These third of the villages, 5% of the people will be chosen at random. These third of the villages, 5% will be chosen by the most connections. And this third of the villages, 5% will be chosen according to this friendship nomination trick. And then we could give you an intervention and then watch everyone in the village to see if they adopt the practice. And what we found was that if you look at days since initial targeting, here we have a multivitamin intervention. We found that nomination targeting dominates random targeting and in-degree targeting. There's actually more going on in this paper, but I don't have time to discuss it today. This was published a few years ago if you want more details. But this paper got us very excited. And so we went to the Gates Foundation and we said, we want to do this on a larger scale and test many more ideas. And so we then moved to the Western Highlands of Honduras and did a huge experiment of 30,000 people in 176 villages. We've had a battalion of people, too numerous to mention in my lab, that have been working hard on this project for years. And we had a 2x8 factorial design. And what we did is we had 2 targeting methods, random targeting and friendship nomination targeting, and 8 targeting percentages from 0 to 100%. And we had 11 villages in each cell. Okay, so we had 11 villages in each of the 2x8 possible combinations of targeting fraction and targeting a strategy. And our prediction was that if you look at the percent in the village targeted from 0 to 100% here, and the percent of the village at the end of the experiment that will have adopted the practice from 0 to 50%, because you never imagine that everyone will adopt. If you have a linear response of no social effect, you have, as you double or the number of people that you treat, you double the number of people that respond. So 40% of people treated, 20% respond. 80% of people treated, 40% respond. But we all know that its social influence is not linear. There's a kind of S-shaped diffusion of innovation. And so there's a social effect. And at low targeting percentages, the non-adoption of other people in the community suppresses your probability of adoption. So you have below the curve until you reach a critical threshold, and then you have this exponential rise, you boom, and now the social effect that previously worked against you now works for you. It lowers your threshold for adoption because everyone else around you is adopted. And our question was, if we use friendship nomination technique, could we shift the curve to the left, right? Could we find, for example, that targeting 20% of the people using the friendship nomination technique was as good as choosing 100% chosen at random? And this would have big impact for how global health interventions were done and the cost effectiveness of those interventions. We're still working on the results, unfortunately, of that paper, but we did what we said. It's true. In other words, it works. Here's just one illustration with I think this was Chupon. This was a Fajero. I'm sorry. This is to get women to stop wrapping the umbilical cord of their babies in this gross cloth, which can contribute to infections. And what we found was that if we used the friendship nomination technique, we could shift them to the left in terms of knowledge about this practice and many other similar results. And then we wondered, well, could we improve on this method? Because our field experience in Honduras was a bit awkward, because we would go into a village and we would say, who are your friends? And you would say, they're your friends. Thank you very much. I'm going to go give her this intervention. And you're like, wait a minute, what about me? So we thought, well, what if instead we picked half as many people and we treated you and your friend? And that might not only keep all the benefits of response to treatment among the untreated, but give us a little kick with response to treatment among the treated. You might be more likely to adopt if I treat a couple, if I do pair targeting rather than friendship nomination targeting. We could shift the curve perhaps still further to the left. And so with support from the Tata Foundation, a Tata group as part of the Yale Tata Alliance, we just published this experiment last month in India, in Mumbai. We had 50 residential communities. These are sort of lower income, not abject poverty, but sort of low middle class, communities in India. And we had anemia education and coupons to buy iron fortified salt to prevent anemia. We had 3 strategies: random targeting, friendship targeting, and pair targeting. We always targeted 10% of each of the 50 units. And then we measured adoption of iron fortified salt and so on. And it worked. It worked beautifully, actually. This is an illustration of 3 of the so-called chawls. These are 3 of the 50 residential units. This is 61 women in this unit, and we chose 12 targets that are shown in red. I think. Let me see how I indicate the colors. Yeah. So the red colors indicate the targets, and the blue colors indicate whether they are chosen at random or not, and the size indicates whether they responded to the treatment or not. And here, all these 3 chawls are about the same size. The number of targets is all about the same, but the number of adopters goes from 7 in random targeting to 12 in friendship targeting to 21 in pair targeting. So we get much bigger response. So pair targeting is even better than friendship nomination targeting. Okay, I have one more experiment to show you, and then I'm going to close with some final remarks. This is another time when I went scrambling into Dan's office for discussion about abstract graph coloring. This is an experiment that Hiro spearheaded that was published 5 years ago now. In this experiment, we brought people into a graph. I'm trying to remember, I think we generated these graphs with a bipartite. I can't remember how we generated these graphs. Doesn't matter. It's in the paper. And we gave the human beings the challenge of solving the graph coloring problem. So each person had to pick a color dissimilar from their neighbors. And if they picked a color dissimilar from the neighbors within 5 minutes and they all converged in a solution, they were paid. So they had to work together to coordinate to solve the problem. So they could pick yellow, orange, or purple, and the graph is shown here. The underlying ties are shown in purple, and the color conflicts are shown in red. So these two orange nodes are in conflict. They have the same color. This node, this orange node should change to purple. And if this person changes to purple, it will resolve the conflicts, and that's a good thing. But there might be other conflicts elsewhere in the graph. All right. So the group had to work together, and if they solve the problem within 5 minutes, they get paid. So this shows here the objective function on the y-axis, the number of color conflicts, and on the x-axis is time. At t0, there are 12 conflicts, and the people are walking through the network until they, each of them is changing their colors whenever they want, trying to solve the problem. They only have local knowledge. They only know what their neighbors' colors are. They don't see the whole graph. They can't know that. And then they get to this situation and they're stuck. These two yellow nodes are in conflict, but they can't choose either of the other colors. This is an unresolvable conflict as compared to a resolvable conflict. The yellow conflicts are resolvable. The orange conflicts are unresolvable. So one of these people has to make a counterintuitive move and increase the conflicts in their neighborhood. One of these people has to do something that seems against their own interests or the group's interests. But if they do that, maybe they'll unlock a solution for everyone else, and that's exactly what happens. And now by 245 seconds, the group has no conflicts, and they get paid. And because we're sneaky, we added to these groups some bots. So we replaced 3 of the humans with bots. And what we did in this experiment is we wanted to study. So my lab is not a computer science lab. We're not able to invent super smart AI like Drago and Amin and others, to replace human cognition. We're instead working on developing dumb AI to supplement human interaction. Because the humans are smart, all we need is some little dumb bots endowed with very simple AI interspersed within this human group that acts like a catalyst that lowers the activation energy for achieving a better state. So all we did in this thing is we added 3 bots that had a little noise. So every 1.5 seconds, they looked at their neighbors and they picked a color with the least conflict. And then 1 out of 10 times, they picked a color at random that might increase conflicts. And that's the amount of noise. So we had 0% noise bots, 10% noise bots, or 30% noise bots. And then we experimentally manipulated whether they were put at random in the graph, put in the center of the graph, or put in the periphery of the graph. We had 4,000 people in 230 groups. The control group, which had just humans, is shown in orange. And here on the x-axis is the time. And on the y-axis is the probability that the group has not solved the game. At time 0, 100% of the human groups have not solved the game. But as time goes by the end, I don't know, 66% of the human group had solved the game. And it turned out, in other branches of the experiment, when we added some bots, we could improve that substantially if there were 10% noise bots that were put in the center. Less noise was not helpful, and more noise was not helpful. And it wasn't helpful if they were randomly positioned or on the periphery. It was helpful if they were in the middle. And kind of a metaphor for this is that if I imagine that I have a huge plain with hills and a mountain, and I take 4 humans and I drop you at some random spot on this surface, and I handcuff you together and I blindfold you, and you're each looking in the 4 cardinal directions, and I say, go to the highest mountain. And you talk among yourselves and you say, well, why don't we each take a step in our direction and report back on the altitude? And north says it's uphill from where I am. And east and west say it's lateral. And south say it's downhill. So the 4 of you move together 1 step north. And then you do the same thing again, and a step west and a step north. And you navigate till you all say it's downhill from here. Have you reached the highest mountain? In this plain with hills and a mountain? Unlikely. No, unlikely. Thank you. You've just reached the nearest hill, right? And now, will you ever reach the highest mountain? No, you're trapped because you can never go downhill. You all say that's suboptimal. So you've locally optimized, but globally suboptimized. In order to find the highest mountain, you need some noise. You need to tolerate some counterintuitive moves where you take a step downhill. And if you have just enough noise, you might have occasionally a sequence of downward steps that gets you back onto the plane, and then you might climb another hill and another till you get to the highest mountain. And there you might stay because that mountain is so high, even if you take 10 steps downward, you'll just loop around and oscillate amongst the global optimum. So we were able to show that that is exactly how it happens. I'm going to skip the next slide, which has to do with the chromatic polynomial. I'll just say, for those of you that know what that is, which is that the bots were especially helpful when the problem was hard, when there were few solutions, when there were the chromatic polynomial was low, the bots were especially helpful. Then when it was many solutions to the graph, the humans didn't really need the bots as much. So we're continuing to experiment on this. We just had a new postdoc join the lab. Atsushi is in the back. He's doing a super cool experiment on optimizing human creativity using bots. But we've looked at coordination, cooperation, communication, evacuation, navigation, and sharing. These are all collective action challenges. And the question is, can we use bots to increase a thing? And Matt, who also just joined the lab, did a whole thesis on the graph coloring problem. If any of you are interested, he's right over here. Okay, let me close with one final idea, I think, on schedule. That was very fast. I apologize. I tried to tackle too much. Did you learn something? You saw something? The students, I don't mean the faculty. That would be very, I didn't mean it paternalistically, but to the students, I feel it's okay for me to be a little paternalistic. Anyway, so let me close with one final idea, which is what it means when we intervene in a social network. Because I think such interventions provide us with a way to manipulate what's known in sociology as social capital. Actually, we're pleased to welcome today Timothy Brick, who is the rector of the Kiev School of Economics, who's here from Ukraine, who's a fellow sociologist and is here for just a few days. So social capital is a deep idea from sociology that's very interesting to me. And to understand this, or get a sense of this, consider this idea. What's the point of a connected life? How does it help us as individuals and as a species? And it turns out that networks are a resource that we can all use. They're a kind of social capital. Now, most people, when they think about capital, think about money. But really, capital is any stock of resources that you can put to productive use. That's what capital is. It's a reservoir of wealth that you can do something with. And two further key ideas about capital are that in order to create capital, you have to invest skill and effort. You have to know something and do something to create capital. And more important and more subtle, and in an idea that's been keeping me awake for 20 years now, is that fundamentally the capital creation process is about the transformation of the natural world. That when you convert one thing to another thing, that's what it means to create capital. That actually capital creation is the transformation of one thing into another thing. What do I mean by that? Well, consider this farm. You invest skill and effort, and this forest. You invest skill and effort, and you transform it into a farm. And the farm is more valuable than the forest because you can do things with a farm you couldn't do with a forest, namely grow fruits and vegetables and grains and flowers, for example. So you invest skill and effort. You transform one thing into another thing. It endows it with this productive power and makes it a reservoir of wealth. Or consider this idea. You could take this tree and invest skill and effort and make it into lumber. And the lumber is more valuable than the tree because you can do things with the lumber you couldn't do with a tree. Namely, invest still more skill and effort and make a violin. And the violin is more valuable than the lumber because you can do things with a violin you couldn't do with a lumber, namely make music. So at every step of the way, you transform one thing into another, and that makes it a stock of productive power and a kind of capital. Well, in the 1960s, principally advanced by Gary Becker and other economists, it became popular to think about human beings as a kind of human capital. So this is a former graduate student of mine who's now a professor at UMass Amherst. And here he is. He's a dissolute drunkard, okay? Notice the toothpick in his mouth and the six-pack here. You can invest skill and effort and clean him up. And now he's more productive and capable of doing things he wasn't previously able to do. such as you can invest still more skill and effort and give him an education. Here he went to Columbia, unfortunately, but anyway. And so now at every step of the way, what you're doing is you're working on the neurons of his mind. In principle, that's what I'm doing right now. I'm investing skill and effort, and I'm transforming your minds. I'm making them capable of doing things they weren't previously able to do. And that's what the capital creation process is all about. Here with human capital. Well, just like physical capital is created by a change in the material world, and human capital is a change in persons, social capital in organizations, in companies, in communities, in villages, in our whole society, is a change in the relations among persons, a change that renders the group more productive and capable of doing things it was not previously able to do. And that is the deepest account I can give you of what social networks mean for our lives and why it is and how it is that we can use them to make our world better. Thank you. That's it. Now, I'm happy to stay. I use up all my time. If you have to go, you should go, but I'm happy to take some questions if people want. I ordinarily don't put that much in a 1-hour talk, and I allow plenty of time for questions, but I didn't have enough time last night to shorten the lecture. So you guys know the famous saying by Mark Twain, I would have written a shorter essay, but I didn't have the time. Exactly right. Any questions for me? You all know who I am. My office is right here. If any of you need me, just come.